Kids, it's the last video of the year. How crazy is that, right? Can you believe it? Well, as we've said many, many times, we are very, very proud of you all. Way to go. Especially, I know where many of your classes are done and you're focusing on APs as well. And this is a priority. I know it's not as high as a priority as you're studying for your APs, but it's still a priority you have to deal with. So good job in practicing juggling many of your responsibilities. All right. Fundamental theorem of algebra, right? So who knew there was a fundamental theorem of algebra, right? Well, there is. And actually, the proof of the fundamental theorem of algebra took centuries. It was started with Euler and maybe even before that. I can't quite remember. It might have even gone back to ancient times where the proof of this was tried to develop. But it really wasn't until Argand, right? The guy who came up with the complex plane. I think he's the first one to have done a serious proof of this. But I want you to digest some of these words because it looks overwhelming, I know. Okay, non-zero, all right, got it, not a zero. Single variable, that means that a single independent variable. So y is equal to x crap. You cannot talk about the degree of some function unless it's a polynomial. Then this might throw you, complex coefficients. But remember from the 18-wheel song in AAF, the real numbers are a subset of complex. So all the polynomials you've been dealing with have technically had complex coefficients, right? It's just, we don't need to call them complex because, well, they're all real. So it's a little bit more efficient to just call them real numbers. Some of the theorems that we use, like the discriminant, something like those, some of the theorems that we use start off with the hypothesis, if the coefficients are real, then these things follow, right? So this theorem, however, does not require that. So multiplicity refers to your zeros or your roots, right? And it's if you have a repeated factor, it counts as many times as that factor is repeated for the roots. All of these polynomials of degree n have exactly n complex roots. And remember, complex also means real. So think about your algebra 1, x squared plus something, right? Very simple parabola that opens up. I've made it equal to 0 to correspond with the x-intercepts. So you used factoring in Algebra 1 and inspection to find the two real numbers, -2 and 2, that you can plug into x squared minus 4 and you get 0. And because x is squared, there are only 2 zeros. And those zeros are real, happens to be. They're also complex, but they happen to be real. This parabola, x squared plus 0, only has one x-intercept, but they are 2 zeros because the factor 0 is happens twice, right? So that's the 0 with multiplicity, an x-intercept with a multiplicity of 2 to match the fact that there are still 2 zeros. But then you ran across x squared plus 4. And at some point in Algebra 1, you were taught to use the quadratic formula. You did the quadratic formula on something like this, and you got a negative under the radical, and you said, oh, negative numbers don't exist in the set of real numbers. Therefore, there are no x-intercepts because I am graphing this parabola on the real Cartesian plane. X is 0. X is a real number line and y is a real number line. There are no x-intercepts. However, by the fundamental theorem of algebra, there are still 2 zeros. They just aren't real. And it wasn't until we taught you how to manipulate with I, you got that negative under the radical, but you could suck that I out and you could represent the zeros as true complex non-real numbers, not true complex, just non-real numbers. But the fact is you could still plug in those non-real numbers in for x. We taught you how to square with I values and add 4, and you were still going to get 0 with both of those non-real zeros. And that's what it means to have a complex root. You can have real roots. -2 can get plugged in to -2 squared minus 4, and you'll get 0. 2 can get plugged into 2 squared minus 4 and get 0. 0 can get plugged into x squared plus 0 and get 0. plus and minus 2i can get plugged into x squared, add 4, and you will get 0. Then in AAF, we moved on to not just quadratics, we moved on to higher order polynomials. And we said, oh, this is an odd degree polynomial. Therefore, the ends behave like a line. Therefore, there is guaranteed to be one real 0. And hopefully you can see that that is -2 on the Cartesian real number lines. But by the fundamental theorem of algebra, there are 2 more zeros. They just aren't real because you don't see any other x-intercepts. And in AAF, what we taught you, right, with the skill of long division, we taught you that long division was one way to also get the non-real zeros. As long as you were given an integer root, or you could use your calculator to find an integer root, you would then use long division to find the rest. Right? We called that depressing your polynomial to a degree 2 so that you could use the quadratic formula and work with your I, right? The i's and the negatives under the square root and find the non-real zeros. Nevertheless, you would take the non-real zeros, including -2, plug them in for x, cube them, add 8, and you would get 0. That's what it meant to solve, right? Values you can substitute into the equation to get whatever's over here. And in this case, it was 0. That's what it means to solve. What about now somebody eventually at some point during AAF, somebody would say, well, what about if I don't have an integer root? Or what about if I don't have any real roots like x to the 4th plus 4? How do I find those complex zeros? And I shrugged my shoulders and I said, oh, I don't know. Well, how you find them is what we're going to do now, which took a lot more prerequisite knowledge, part of that being polars. So what does it mean to solve an equation over the set of complex numbers? That means you can't just take this and say my solution is -2. Yes, in the set of real numbers, that is one solution. But since I have complex zeros, non-real zeros as well as real, I notice I replaced the x with a z. And then I moved the 8 to the other side. And I said to myself, what numbers can I cube and get -8? And then I said, wait a second, I'm also cubing non-real numbers and getting -8. Who's knocking at my door now? Well, Demov! Oh, it's not Pythagoras this time. Thought it might be Pythagoras, but it's not. It's Demov. Don't forget that inside Demov is Pythagoras, so he's always knocking at your door. What numbers can I cube and get -8? I don't know. And remember, I don't have long division. I don't know how to do this. I know how to get one real 0. I don't know how to get the others when I'm restricted to the real number plane. So I think I'm going to go to a different system. I thought about Moivre and I started translating people. Z is also known as r cis theta. -8, right, is a real number, but I can turn it into a complex number by -8 plus 0i. I also know how to graph that. Thank you, Argand. I know how to graph that not on the xy plane, but on the real imaginary plane. What number can I cube and get -8 plus 0i? Here is -8 plus 0i. Now that's in rectangular. I have an equal sign and I have polar. But I know how to take, let's get rectangular into polar. How do I get rectangular into polar? Well, I know how to crank this out. -8 squared, who cares if it's negative because I'm going to square it, plus 0 squared is just 8. And then what's my angle? Can you see it? But, right, 0 over -8, right, that's going to be pi. So now I have polar on the left and polar on the right. I have an equal sign. Oh, hey. How did I get from r cis theta cubed to r cubed cis 3 theta? Oh, de moi, thanks. That's how I did it. Now, I've been highlighting this equal sign for a reason. What's on the left is the same as what's on the right. That's what it means to be equal. It is the same. I have a polar expression on the left and a polar expression on the right. The real part on the left must be equal to the real part on the right. The argument on the left must be equal to the argument on the right. So look at what that gives me. But I can isolate r and theta so that I now really am isolating z. I'm getting z by itself. I'm undoing the cube just like I did in Algebra 1. I just had to, and when I undid, right, basically I raised both sides to the 1/3 power and I got -2. I got the real 0 by just saying x cubed is equal to -8, take the cube root of both sides. And I got -2. That's swell, but that doesn't give me my non-real zeros. But I just did, because in polars, what does not r cubed, when r is 2 and theta is 3, what does that represent as a polar number? 2 cis theta. 2 cis theta. Can you now take me back into rectangulars? Can you take me back to rectangular? Right, how do I go back to rectangular from here? Right, going back and forth. That's 2 cosine pi over 3. Thank you, Speed Trig. Pi over 3 is in the first quadrant. Cosine of pi over 3 is 1/2. Sine of pi over 3 is √3 over 2. That's all multiplied by 2. 2 times 1/2 is 1. 2 times I √3 over 2 is I √3. And I can graph that on the Argonne plane, right? This is 1, and this is √3, which is 1.7-ish, I think. This radius is 2. If you cube this, 1 plus √3i, if you cube it, you will get -8 plus 0i. This is one solution over the set of complex numbers. I already know -2 is a solution, but wait a second. How many solutions am I supposed to get? And let's pretend I didn't have algebra even to get me my real root. Let's suppose they were, how many am I supposed to have? By the fundamental theorem of algebra, how many zeros am I supposed to have? 3, and I only found 1. And I found 1 in the first quadrant. But do you remember what I did here? I erased it. But when I first graphed -8 plus 0i and I was figuring out the angle graphically, and I said that's pi, what was to stop me, hello AAF and coterminal angles, from doing this? That's 2 pi times 1, or 2 pi times 2, right? So if I want more solutions, I just have to add more revolutions of 2 pi. We'll say k is an integer, and we'll just stay with the positive integers. I mean, I guess we could go backwards, but I'm just going to be repeating. And I'm going to start with the integer 0. Do you see why? Right? Look at my solution here. When k is equal to 0, this fraction goes away and I get my first solution. But can you get your other ones? So I did k is equal to 0. I did k is equal to 1. Do you see what I did there? If k is equal to 1, that's 2 times 1 times pi, which is 2 pi, plus 1 pi all over 3 is 3 pi over 3. Then I did 2. 2 times 2 is 4. 4 pi plus 1 pi is 5 pi all over 3. Then I did 3, and that's 6 pi plus 1 pi, which is 7 pi over 3. Oh, wait, 7 pi over 3 gets me to the same place. Again, coterminal as pi over 3. So I could stop at 3. But I got myself an answer, 3 answers. Oh, I was supposed to get 3. So this is Z2, and this is Z3. Wait a second, I thought I already had one of my zeros. I thought that was -2. Oh, snap. What is 2 cis pi? Sine of pi is 0, thanks speed trig. Cosine of pi is -1, thanks speed trig. -2. Oh my God! This method got me my non-real and my real zeros by the exact same method. Got all 3. How about 2 cis 5 pi over 3? What is that? Two cis 5 pi over 3 is 2 times cosine 5 pi over 3. Thanks, speed trig. Cosine of 5 pi over 3 is in the 4th quadrant. Cosine is positive, but sine is negative. I'm multiplying everybody by 2. 2 times a half is 1. 2 times -√3 over 2i is -√3. The conjugate that you would have gotten with long division. Right? So here's Z1, here's Z2, here's Z3. I already graphed Z1 here on the argon plane. Which one's that? That's 1 and negative. Oops, sorry. -√3. And then where's this one? This is -2 plus 0i. There's that one. So here is Z2 and Z3. If you cube any one of those, guess what you're going to get? If you plug in -2 plus 0i, you're going to get -8. If you plug in 1 plus or minus √3 and cube it, you will get -8. That's freaking nuts. Math is pretty cool, I have to tell you. Also, check this out. Right? Does that make sense? What's true about the radii of a circle? They're all the same. Is the length of Z1, Z2, and Z3 all the same? Yes, because what's their radius for each one? 2. Oh, snap. Right? All right, so that was solving really what looked like an equation in the set of real numbers, right? Right? We had x cubed plus 8 is equal to 0, but we solved it over the set of complex numbers. What about a straight up complex equation? Z cubed is equal to 8i. Can we use the same thought process? Yes, we can. What number can I cube and get 8i? I'm cubing powers. In non-real numbers, I think de Moivre. So I replace z with its polar form, r cis theta. I want to cube it. 8i, I put in rectangular form, and then I'm going to turn it into what? Right? I'm going to turn it into polar form and graph it on the argon diagram. So do you see in this case, right? On the imaginary, this is 8 on the imaginary plane and 0 on the real. What angle is that? pi over 2, right? The reason, right, sometimes when you picture, because I get kids that'll do an algorithm and they know how to get r. R is equal to the square root of 0 squared plus 8 squared. Well, that's the square root of 64, which is 8. And then they'll try to do theta, and theta is inverse tangent of 8 over 0. And they'll go, well, that's undefined. Stop. The algorithm brain. Algorithms are very important. Recipes are very important. But you have to know when to turn off the recipe or the algorithm brain and turn on the analysis brain. If your analysis brain has to be on the entire time, you get worn out, you get stressed, you get overwhelmed. That's what the algorithm brain is for. Muscle memory. I don't have to think about the formula for inverse tangent, right? Or to make y over x. But now I have to analyze 8 over 0. What does that mean? Who has a tangent of a number in the numerator that's not 0 and 0 in the denominator? That's a pi over 2 issue. When the 8 is positive, that's a pi over 2. If the 8 was negative, it would be 3 pi over 2, right? So there are some educational people that'll say, oh, memorization is terrible. Everybody should just learn by discovery and then it'll have more meaning. That's exhausting to have to discover everything. I want the recipes. I want the algorithms, but then I want to be taught how to analyze as well. So don't forget the analysis piece. So when I'm turning this into, yes, I used a formula, but I also thought. So notice to go from here to here, I used a Moivre, right? That's r cubed cis 3 theta. And then go from here to here, right? I used my conversion from rectangular to polar with analysis. Now I'm going to use my algebra brain. I have an equal sign. Therefore, the real components must match up. And the arguments must match up, only because I have an equal sign. So what do I say? R cubed is equal to 8. Notice I make these, I don't have to make that number nice, right? If it's, let's pretend that this had been 2i. Well, then when I got r by itself, it would be 2 to the 1/3, not an integer. Just leave it 2 to the 1/3. But I'm starting off these examples where I got a nice number, right? So the cube root of 8 is an integer, 2. Divide theta by 3, and I had theta pi, 3 theta was pi over 2, so theta must be pi over 6. So turn that into my polar number. That's one of my solutions. Oops, sorry. That's Z1, but Z1 is in polar form, so I'm going to turn it into rectangular form. Thank you, Speed Trig. Right? Cosine of pi over 6 in the first quadrant is root 3 over 2. 2 times root 3 over 2 is root 3. Sine of pi over 6 in the first quadrant is 1/2. 2 times 1/2 is 1. There is my first rectangular 0 of this complex equation. Right? I could also write this way, right? Z cubed minus 8i is equal to 0. Let's graph that on the Argonne plane, right? Root 3, which is a little bit bigger than 1, and 1. If you cube root 3 plus 1, you will get 8i. You will get this length, right? It should be longer, right? How do I get the other ones? Stop, think about the fundamental theorem. You're cubing, so how many zeros should you get? 3. So use your 2k pi. Since you want 3 zeros, always start with k is equal to 0 and use 1 and 2 to get your 3 zeros. You could keep going, but you'll just get repetitions. So what am I going to do here? I'm going to plug k is equal to 1. Oh, crap. I need a common denominator, don't I? This time. I didn't need that before. This denominator is 6, so multiply this by 2 and that by 2. So I'm going to get theta is equal to pi plus 4k pi all over 6. I already plugged in 0, and that got me pi over 6. Now I'm going to plug in 1. When k is equal to 1, this is 4 pi plus 5, which is 5 pi over 6. Then I'm going to plug in 2. 4 times 2 is 8. 8 pi plus 1 pi is 9 pi over 6, which of course is 3 pi over 2. I turn these into rectangular, right? 2 cosine 5 pi over 6 plus I sine pi over 6. Thank you, speed trig. And that's where I got negative roots because 5 pi over 6 is in the second quadrant, so cosine is negative, sine is positive. Multiplied by 2 eliminates the denominator of 2 on both of these. This is 3 pi over 2. Cosine of 3 pi over 2 is 0, bye-bye, plus I sine 3 pi over 2. Well, sine of 3 pi over 2 is negative 1. Negative 1 times I is negative I. Negative I times 2 is negative 2I. Wow. There is my second 0 and my third 0 of this complex equation. If I were to graph those, ooh, that's probably a little too long, isn't it? This is negative root 3, 1. Probably should have stopped there. And then what's negative 2I look like? That's 0 plus negative 2I, so that's going to go down on the negative y-axis. And then look at the beautiful symmetry, right? Because what is the length of each one of these radii? I mean, just like the last one, because I still used 8. Cool, right? Cool. So, de Moivre's theorem to find roots. If you have a complex number that is raised to the n power, right, as long as z is complex, so I should write this to the n. Well, no, I don't. No. To get z by itself, you need to take this rectangular into, to use de Moivre, into polars. And then you take it into polars, and then you have this then becomes r cis theta. Right? Rectangular to polars, r cis theta. And to get z by itself, in other words, to undo the power, right? Z to the 1 over n becomes r to the 1 over n, cis, whatever your original angle was, plus 2k pi over n. Right, where your n is that. So let's try. I wrote both of these because they're the same question. Find all roots of x to the y equals x to the 5th plus 32. Roots means make this 0. Which again, I know it's 2 to the 5th is, negative 2 to the 5th is negative 32, right? Because I'm going to say, oh, that means negative 32 is equal to x to the 5th. I know one real 0 is negative 2, but I don't know any of the other ones. Or finding the 5 fifth roots of negative 32. It's the same question. So what do? I say z to the 5th is equal to negative 32 plus 0i. Right, there's my z to the n is equal to rectangular. Take that rectangular to polars. And notice that I'm going to use 0, 1, 2, 3, and 4, right? Because as the theorem says, you need to stop one shy of your power, right? Again, you can keep going. You're just going to then cycle, and you're gonna repeat roots. So you don't need to do them over and over again. And it's n minus 1 because you're always starting with 0. So what do I get out of this? Bam. How the heck did all those happen? Firstly, r to the 5 by the fundamental theorem of algebra means I am going to find 5 zeros. I already know I'm expecting one of them to be -2, right? I know there's one real one in this case. So what did I do? I plugged in 0 here, and that's where I got pi over 5. Then I plugged in 1. 2 times 1 is 2. 2 plus 1 is 3. That's where I got 3 pi over 5. Then 5 pi over 5, 7 pi over 5, and 9 pi over 5. You do not have to take these into rectangular unless you are asked to, right? I can leave them in polars. Unless you are asked for rectangular or you're matching multiple choice. But it is a nice check for you to say, hey, I know that -2 raised to the 5th is equal to -32. So one of these 5 has to be -2. Can you find it? Oh, snap, there it is. That's 2 cosine pi minus I sine pi. Sorry, plus I sine pi. But sine of pi goes to 0. 0 times I is 0. Cosine of pi is -1. -1 times 2 is -2. Woot, woot. I didn't bother graphing this on the Argand plane. But if I had, oh, geez. If I had graphed this on the Argand plane, everybody would have every spoke of the wheel would have a length of 2. And then I would have a first quadrant, a second quadrant, -2 with a 0 I, a third quadrant, and a fourth quadrant. Right? And more importantly, conceptually, if you took any one of these complex numbers, either in polar or in rectangular form, and you raised it to the 5th power, you would get -32. Obviously here, you would get, right, Z3 was equal to -2. Was equal to -2. Raise it to the 5th power, raise this to the 5th power, and you're going to get -32. Remember, -32 is actually -32 plus 0 I. So that's way out here, right? -32 plus 0 I. If you cube any one of these 5 spokes, you will get that purple spoke. Crazy. All right. We will do some more of this and start reviewing for our test in our next live session. See you then.